We have arrived at the last section for Unit 1. In Section 1.4, we will study linear systems and matrices. So again, let's pause and consider the progression of topics that we've studied in Unit 1. We began with a linear equation in one variable. An example of which would be 2x plus 3 equals 5 with a single solution x equals 1. Then we went to an inequality in one variable, such as 2x plus 3 greater than 5. The solution to a linear inequality in one variable is an interval of solutions or an infinite number of solutions, and generally we express that in interval notation. Then we bumped up to linear equations in two variables. If we consider one in standard form, 2x plus 3y equals 5. The solution to a linear equation in two variables would be an ordered pair. For example, x equals 1, y equals 1 is an ordered pair solution, but we know there's actually an infinite number of solutions to that equation, so we graph those as a straight line. So whatever that line looks like, every single point along that line would be a solution to that equation. Today, we're going to move into linear systems. So we're still working with two variables, we're still working with lines, but now we're going to be looking at a pair of equations. So section 1.4.0, System Introduction. A system of equations is a collection of two or more equations. For example, a linear system of two equations in two variables looks like 2x plus 3y equals 7, 3x minus 4y equals negative 32. A solution to a system of two equations in two variables is an ordered pair, and an ordered pair looks something like this, x coordinate, y coordinate, that satisfies both equations simultaneously. So our goal in solving a system of linear equations in two variables is to figure out the ordered pair that balances both of those equations at the same time. Keep in mind, each of those equations graphs as some sort of straight line. So when we solve a system, we're graphically looking for the intersection point, the ordered pair that balances both equations, or the intersection point of those two lines. To solve systems, we have several methods. In section 1.3, the very last example we considered, illustrated solving systems by graphing. If I can graph both of those lines and identify the intersection point, then I've solved the system. Today, we're going to consider an algebraic method for solving systems, elimination. We will also learn how to solve systems with matrices in our calculator. So let's consider an algebraic solution to a system of linear equations in two variables. This method is called elimination. In other classes or previous texts, you may have also heard this called addition. Those two are one and the same. So we'll run through the algorithm, or the set of steps, for solving a system of two equations in two variables algebraically by elimination. And when I say algebraically, I simply mean we're going to manipulate the equations to find the solution as opposed to graphing the two lines. So the first step is to be sure that both of our equations are in standard form. So step 1, if necessary, rewrite both equations in standard form. Which, remember, was ax plus by equals c. Remember, we had slope-intercept form. Slope-intercept form was y equals mx plus b. In slope-intercept form, the y was isolated. That's not what we're looking for here. We want both equations in standard form. Number 2, multiply one or both equations by a constant a non-zero constant, so any number but 0, multiply one or both equations by a constant to achieve opposite coefficients for one variable. That's probably the most complicated or challenging step. So what do I mean by that? Let's just take a quick peek down here at example 1. You can choose to eliminate either x or y. In example 1, I would choose to eliminate x. So I'm going to look at those two terms. My goal is to obtain opposite coefficients. So I notice that equation 1 has a coefficient of 2. So my goal would be to get a coefficient of -2 in that second equation, because positive 2 and negative 2 are opposites. So my goal here is to get a coefficient of -2. Okay, so that's what I mean by achieving opposite coefficients. So we'll come back down and work this example here in a few minutes. Let's continue our algorithm. Once I achieve opposite coefficients, next step is easy. We're going to add the equations together, term by term. Now remember, if one of our variables has opposite coefficients, that means when I add them together, they're going to cancel out and make a 0. The result will be an equation in one variable, and that's where we started Unit 1 with, solving linear equations in one variable. So number 4, solve the resulting equation in one variable. That's going to give me half of my solution. Remember, my goal is to find an ordered pair solution that balances both equations simultaneously. So once I know the result of one variable, I'm going to use it to find the value of the other variable. So step 5, we're going to use something called back substitution. Back substitute to find the value of the other variable. And you know what? I need a step 6 here. So let's add step 6. Check. We're going to check by substitution. So let's get back to example 1. We discussed how we needed to get opposite coefficients for one of the variables. It's convenient to get an opposite coefficient on x in example 1a because I've got an easy coefficient to work with right here. So I'm going to just copy down equation number 1 as is, and I'm not going to make any changes to that. As we discussed previously, our goal is to get a -2 coefficient for x in equation 2. So I'm going to multiply both sides of equation 2 by -2. That's going to give me -2x minus 16y equals -4. So I'm multiplying each term of equation 2 by -2. Now, if I look at my two coefficients for x, they are opposites. So now I'm ready to add these two equations together term by term. Working vertically, 2x plus -2x is 0x, so the x's cancel out. Moving to the next term, 6y minus 16y gives me -10y, and -1 plus -4 gives me -5. Notice the result is a linear equation in one variable, and we've learned how to solve these. So we're going to isolate y by dividing both sides by -10, and here we've arrived at half of our solution. When we reduce that number, we can see that y is equal to 1/2. So I'm halfway there. I need to find the corresponding x value. This is where we use that process called back substitution. And all that means is I'm going to go back to one of my original equations, plug in 1/2 for y, and then solve for x. Now, let me erase some of my work up here so I can see that original equation 2 clearly. I can use either one of those equations to solve for x, but I want to choose the easiest one to work with. So I'm going to use equation number 2. So equation number 2 was x plus 8y equals 2. I'm going to take the value that we found for y and plug it in right there in this equation. And remember, if you use either equation, you should end up with the same answer from either one. Okay, so we've plugged 1/2 in for y. Let's go ahead and evaluate 8 times 1/2. 8 times 1/2 is 4. And now we have a linear equation again in one variable. So we're going to solve by subtracting 4 from both sides. And we'll end up with x equals -2. So officially, we want to express the solution to this system as an ordered pair. That means in alphabetical order. So x is -2 and y is 1/2. Now, before I put a box around my answer and present that as the result, I want to check this. So I'm going to take -2, back up to both original equations, plug it in for x. We're going to plug 1/2 in for y and make sure that we have a balanced equation. So -2 is going to get plugged in for x. 1/2 is going to get plugged in for y. This looks like 2 times -2. Notice I'm using my little negative and not the minus operation on the calculator. Plus 6 times 1/2. And that result is -1. So that ordered pair balances the first equation. Now I'm going to plug it into the second equation. The second equation is x plus 8y equals 2. So we're going to evaluate x, which is -2, plus 8 times y, which is 1/2, and the result is 2. And that's what we had on the other side of our equation. So now we're confident that -2, 1/2 is the ordered pair solution of those two lines. What does that mean graphically? If I were to sketch the graph of those two lines, they would intersect in the ordered pair -2, 1/2. Now here's a quick pop quiz for you. Can you tell me in which quadrant would those two lines intersect? In which quadrant would those two lines intersect? So remember, in our coordinate plane, we label the quadrants in a counterclockwise direction. There's quadrant 1, quadrant 2, quadrant 3, and quadrant 4. If the intersection point is -2, 1/2, if x is negative and y is positive, looks like they would intersect in quadrant 2. Hope you got the right answer on that one. Okay, let's try another example of solving systems by elimination. In our second system, this one's a little bit more of a challenge because unlike the first example, neither of our variables has a coefficient of 1 in either equation. Now remember, you can choose to eliminate either x or y. I'm going to continue picking on x. So the technique here is to sort of trade coefficients. Okay, if I multiply equation number 1 by 2, let me just jot that in here. Okay, I'm going to multiply equation number 1 by 2 on both sides. That's going to give me a coefficient of 10 for x. I'm just picking on x for a minute. So if equation number 1 has a coefficient of 10 for x, then my goal would be to get a coefficient of -10 for x in the second equation. So to achieve that, we need to multiply by -5. That would give me a coefficient of -10x in the second equation, and we would have achieved opposite coefficients. So notice I took the coefficient of x in that second equation. Let me clear all this off. I took this coefficient and applied it to that equation. I'm going to take this coefficient and change its sign and multiply it by this equation. Okay, so let's go ahead and write this down. We're going to multiply equation number 1 by 2 on both sides. And I'm going to multiply equation number 2 by -5 on both sides. Hey, by the way, if I had chosen to multiply equation 1 by -2, then I would multiply equation 2 by positive 5, whatever it takes to achieve opposite coefficients. All right, let's carry out this multiplication. So distributing our 2 in that first equation, we have 10x minus 12y equals 2. Don't forget to multiply on the other side as well. And then we'll distribute negative 5 in the second equation. That's going to get, oops, I wrote down the wrong number there. Did y'all notice that? Let me fix that. That's supposed to be a 2x. Okay, that's going to give us opposite coefficients. So negative 5 times 2x is negative 10x. Negative 5 times negative 4y is plus 20y, and on the right side we have negative 10. We have achieved opposite coefficients for x. Let's add our equations together term by term. Notice the x's cancel out, and we end up with negative 12y plus 20y, which is 8y, and 2 plus negative 10 is negative 8. We can solve this linear equation in one variable by dividing both sides by 8. And we end up with a very simple answer, y equals negative 1. Now, I'm going to take y equals negative 1, which is half of my solution, back to one of the original equations. And again, it doesn't matter which equation we use, as long as we plug it in correctly. So I'm going to choose the simplest one. I'm going to opt for equation number 2. And we're going to replace y with the value that we found, negative 1. So plugging negative 1 in for y, we end up with 2x plus 4 equals 2. That's an equation in one variable, and our goal now is to isolate x. So we can begin that process by subtracting 4 from both sides. We get 2x equals negative 2. Divide both sides by 2. And we have the other half of our solution, x equals negative 1. So as an ordered pair, our solution is x equals negative 1, y equals negative 1. But before we move on, we definitely want to check our work. So I'm going to go back to both original equations and plug negative 1 in for x and negative 1 in for y. We have 5 times negative 1 minus 6 times negative 1. And that result is 1. So equation number 1 is balanced. For good measure, let's check equation number 2. 2 times negative 1 minus 4 times negative 1 equals 2. So since both equations are balanced, we are confident that this is the solution to the system. So again, pop quiz. Without graphing those two lines, can you predict in which quadrant would those two lines intersect? Well, since x is negative and y is negative, looks like those two would intersect in quadrant 3. So this is an algebraic method for finding the intersection point of two lines called elimination.